All right, so this is chapter 8 of Understanding Deep Learning. Um, this chapter will be all about measuring performance. Um, so we start off by looking at this MNIST data set. A lot of you have probably seen this. So this is the standard 2D one where you have your pixels laid out, and then the goal of it is to teach a neural network in order to tell the different numbers apart. So you have 0 through 9, you have 10 different classes. Um, and in this, they actually chose to use a derivative of it, the 1D data set. So it's been sort of simplified to just 40 variables instead of the 28 by 28 that MNIST typically is. It's the same classification though, 0 through 9. Um, so they walk us through this example. It's got 40 inputs, it's got 10 outputs for all the different classes, and then they have 4,000 different training examples, 400 of each class, and then we're training two hidden layers, 100 units each, stochastic gradient descent, batch size of 100, learning rate of zero point 0.1, and 6,000 steps. And then if you want to, you can work backwards from the number of steps and the amount of data and the batch size to figure out the epochs. So it's generally good to actually measure things in terms of steps because if you measure by epochs, the definition of an epoch will change by how much data you actually have. So it's useful to measure by steps. Um, so looking at the training results of this, we can see here's the percent error. So this is like the how many it's getting incorrect, and it's going down over time. You do 6,000 steps, and it gets perfect accuracy eventually. And then you can see a similar curve with the loss. So it's going down over time. It's a little bit noisier, but eventually it goes to a very low value. So after a certain point, it has learned your trading data very, very well. But the problem with this is you don't actually care how well the model can fit the training data. You care how good the model is at making predictions on unseen data, so new data. You want to be able to use this model to look at new data and come to the correct conclusions. And so the way we do this typically is with some sort of held out data, so some test data. So you train on this, you learn from it, and then the other curve is showing here's some other data that we use we never learned from, and we just want to measure its performance against. Um, and so you can see that before on the training data, the curve is pretty similar, but actually on the test data, the curve is quite a bit different. So we can see that the model improves to a certain amount, and then after that, it flattens off. And so the accuracy on the training set continues to improve, but the accuracy on the test set does not improve. And then on the loss side, instead of the accuracy, we actually have a slightly different pattern where the test loss actually diverges. So you train further and further, and the test loss goes higher and higher. Um, and so the reason that this can happen and why these graphs are not perfectly linked is that your training set, it's going to continue to learn these patterns and become more and more confident, and then the loss will diverge because it's confidently wrong and it's pushing further and further in the wrong direction. Versus this, it's on a certain decision boundary and that's not changing, but it's still correct or incorrect. It's not actually changing the decisions that it's making. Um, so then we can break down its error into three separate parts. So one of them is noise. So just saying this black line is the true function of our data, and then the orange dots are the sampled points from inside of that. Um, and then the bigger boundary around that is kind of a representation of the noise and the uncertainty. Um, so we can look at a simple model, and what they discussed in the chapter was basically let's simplify this so that this can be directly solved. So this neural network actually has the first layer, the weights are just frozen. It's just something hard coded, and then the only thing that we're solving for are these final output weights, basically. Um, and what this does is it makes it so that we can just have a certain number of cut points, basically. So it's changing its trajectory at different spots. Um, and so this makes it so that we get a very simple output decision boundary through all these points, and we can also solve for it analytically instead of doing SGD or something else. Um, So the noise aspect of the error can come from multiple different places. So you can have noise in the actual input. So your input can be recorded incorrectly, but you can also have noise in your labels. So if your output is labeled incorrectly, then you can have noise in that way. So you assume that not everything is always 100% accurate even if it didn't come from your model necessarily, there can be inaccuracy in other places as well. And then the other piece of this is the bias. So you can have a model that actually doesn't have enough capacity to perfectly fit a certain curve. So the way that this neural network has been set up, it's only able to do a certain number of these turns. And so if you had a model with infinite capacity, then in theory it could perfectly fit this curve. But when you only have a certain number of um, inflection points, you can only fit it so well. Um, and then looking at variance, variance is saying basically we don't have enough data in order to perfectly represent the entirety of the curve. So every time you fit, you might end up with a slightly different result, or every time you sample from the distribution, you might get a slightly different result. So if you have a true data function that follows this black line and then you sample from it multiple times and there's a certain amount of variance around this point, every time you train the network on that different subset of 10 points, you might end up with a slightly different result. So this is kind of the mathematical formulation saying that here's the full representation of the entire loss, and it actually comes from the various different pieces of the variance and the bias and noise. So one of the things that they were talking about in terms of variance, so if we only have 6 data samples from this function, then we're going to get random points on somewhere along this line, basically. And every single time that we train a model, because we're pulling from different points, we'll get a very different outcome because we only have 6 points actually. And so if you look at these, there's many different ways that you could fit to all of these different samplings of the points. And so you end up with very inconsistent results, basically. And so this was starting with 6 samples. Now this is with 10, and you can see that this is slightly more consistent. We have more points, so the model can more closely fit um, the distribution. Um, and so going even one layer above that, now that you have 100 samples, your model is fitting very consistently because the whole range of potential values is well represented by the data. When you have so few points, there's many different possible ways that you can interpolate to get um, reasonable outcomes from a model given the data. And so how do we reduce the bias? So this is looking at the initial example we had. There's only 3 different regions. And if you increase the parameters of the model, then you can make more of these different regions. And so increasing the parameters of the model, you can go from this to this to this, and now all of a sudden you can fit the curve a whole lot better. When you have a very high bias model like this, it just doesn't have the capacity to even represent a curve that's that smooth. And so the thing with adding more parameters to the model is you can end up with much noisier boundaries potentially. As you over parameterize, then it can fit your data better and better and better, but that doesn't necessarily guarantee that it's fitting the true function of the data. Um, and so this is an example of this, basically showing that as you increase the parameters of the model, you can end up with this pattern where it is perfectly fitting all of the data points, but it's not fitting a realistic curve of the pattern. Um, so yeah, there's a question about overfitting. Yeah, this is an example of overfitting. When you add too many parameters, potentially you can memorize the data, but you can also interpolate in very strange ways where it's not fitting the function of your data. It's just drawing a extremely wiggly line through your data. So people will often talk about this bias variance trade-off because you want a model that's expressive enough that it can fit your points and learn the true pattern, but you don't want it too expressive so that it's just memorizing your training data and not actually learning the underlying pattern. Um, and so you can see that as the model capacity goes up, the bias goes down, and as the model capacity goes up, the variance also goes up. And so you have to take both of these in account and try to figure out the trade-off between these. And so what they're showing is that the best actual model capacity is around here. Um, but in reality, what most people do at this point is they go very high on the model capacity side. It's just a function of how much data you have typically. If you have very little data, then you probably don't want that big of a system. But in reality, a lot of people um, either have a lot of data or can find some way to do something sort of self-supervised or starting from someone else's model that was trained on a lot of data. Um, so in reality, this becomes a bigger problem when you have much more limited data. So this is something that most people working in deep learning don't spend that much time thinking about anymore because the goal is always just get more data until this equation doesn't really matter that much. So another topic that they introduced was this topic of double descent. And so um, there's this concept where you train a model and then it gets to the point where it has perfectly fit your training data. But surprisingly, the test data continues to improve beyond that point. So even though the accuracy is 100% on the training data, it might not be the best possible weights for the test data. Um, and so um, very often you find that scaling the model up further, even though you have a model that can perfectly fit your training data, it's useful to make a model even more over parameterized than that. And people have done some research and figured out that there's this kind of surprising pattern where as you scale the model up, once you hit the exact point where you can perfectly fit your training data is actually not um, a good size for your model because it will fit that training data, but it won't be able to generalize as well as if you actually over parameterized it. Um, so this is what we're seeing here is like right where you get the perfect fit from your training set is actually a poor fit for your test set. And so if you go further along this axis, you actually get better performance. And there's various hypotheses as to why exactly that is. So in the book, they called this the classical or underparameterized regime. So where you don't even have enough parameters to actually fully fit your training data, and then the modern or over parameterized is over here where they're saying we have more parameters than we even need in order to perfectly fit our training data. And then this critical regime is this point here where you're kind of in between. You're not doing better because of the parameters that you have, and it's kind of the high point of the test loss. Um, and so they show this on the MNIST 1D, and then here's the MNIST as well. And you can see that it's even more pronounced here, actually. And they're showing that this actually scales with the amount of label noise that you have. So the MNIST 1D is completely clean, and then this is a version where it has 15% label noise. So they've just swapped the labels on 15% of them to be incorrect. And then on MNIST, we see that it's pretty pronounced. And then we see on the CFAR 100 um, how it changes when you introduce noise. Um, so there's a question about if I've ever encountered double descent. In practice, not really. I have seen loss patterns that are similar to this in some way, where the training loss kind of maxes out, but then somehow the test loss continues to improve. But I haven't typically done so much in terms of the model capacity. So I don't typically even play around in that area where the model's only barely fitting the training data. Typically, our networks are so over parameterized by default that we don't even kind of play with that boundary. We're already so far to the right of that line that it's not even a consideration. Even like a ResNet 50 or some vision model has enough parameters that you're not really worried about it having too little parameters to be able to fit your data.
Yeah, if I could, excuse me, if I could just clarify that point, to make these graphs, every dot on the brown line is a complete full training of the network at a different size. So the only way you can produce this graph is if you train your model 100 times, train different sized models 100,000 times or whatever. So, you know, I would argue that pretty much most of our, if not every neural network that we build has this phenomenon. We're just never going to know because we're never going to train those really small ones like Brian was talking about. We're way on the right edge of the curve, and we're never going to train one small enough to see that it does worse. Because if you know this pattern, then you're just going to go as far to the right as you can based on your time and compute budget.
Yeah, yeah, exactly. And so one point that they want to make is that actually regardless of training loss, so the loss is already zero. It's already perfectly fit to the training data, but we still see that there's a change in the test loss actually, or the test accuracy. Um, and so that's kind of interesting that even for the same loss hitting maximum value, you can end up getting a different outcome and a different generalization. So one of the things that they wanted to point out was the interpolation can end up different when you over parameterize, and the kind of hypothesis that people have is that you end up with a smoother boundary when you have so many extra parameters. When you fit in that critical regime, you have exactly enough to perfectly fit your data points, but you might fit it with some very wiggly line that is just enough to constrain it to hit those points. But if you have so many more parameters, then you end up actually following a much smoother curve. So they're showing here, here's what you get with 8 hidden units, 10 hidden units, 50. Um, and so when you only have 10, you might have this very steep pattern that's way too much. And then when you go all the way over to 50, you might have something that's actually quite smooth and is able to fit your data more faithfully. Um, so this is another graphic showing this. So if you have this sort of middle amount, there's so many ways that you can actually fit this curve. So you only have data from here to here, and then everything in between your model's just kind of interpolating. It's just guessing what can be in between these points. And so depending on the number of parameters that you have, you can end up with something smooth like this, or you can end up with these crazy wiggles that end up not really fitting a predictable pattern. And so there's various different ways that you can mitigate that. And so one of the things that they were talking about is regularization. In reality, typically what you want to do is actually have better data. You want full coverage of these points, but sometimes that's difficult to have. Sometimes getting additional data is not cheap, or it's just difficult to find data in that specific long tail. There, it might be hard to, it's easy to get data points over here, but it's difficult to get data points over here for whatever reason. So that can be a challenge. But in reality, it's just very difficult for any model to say, here's what happens in between this mass of points when there's big gaps in between them, because what's actually in there is what's ever learned from the data. Um, so now talking about the cursive dimensionality, if we think about the data that we had, so that MNIST 1D, it's got 40 input features, and then let's say we have 10,000 data points. Even if we just limited this to only having 10 values, initially we were talking about they had continuous values, but if we say there's only 10 of them, we're still ending up with 10 to the 40 bins, which is a whole ton of bins, and we only have 10,000 data points. And so there's a whole bunch of space in such high dimensions. Um, and in reality, this makes it difficult for us to fit models. But the good thing about this is that typically your model will fall in a small subspace of that huge potential possible area. Um, so we're lucky that typically your data won't cover that entire 10 to the 40. It will only follow some certain piece of that. Um, So there's a lot of weird properties with high dimensional space. So they have some good graphs here, just basically showing that as you go up in high dimensionality, the distance from the origin goes up higher and higher. And the distance between points also goes up very high as well. So if you have very high dimensional space, then you're going to need more data in order to fill out that space. And it becomes more difficult for the model to interpolate, because you have like in that graph we saw, that's only a 2D graph, but we already saw that there's big gaps in that data, and then in between those points you can end up with those extremely wiggly lines. So in high dimensionality, we have to fight that even harder, and we hope that the model is actually interpolating reasonably between data points. And that's part of why we need so much data. Um, so one thing about choosing the hyperparameters, it's we don't have those exact graphs given to us in terms of bias and variance before. So a lot of the times we have to figure out sort of just empirically with experimentation. And the difficulty with this is that if you do repeated experimentation on the same validation set or test set, um, you will end up optimizing indirectly for that validation set as well. Um, so if you run a model 1,000 times and pick the one that is best for your held out data, then what you've indirectly done is you've optimized for that data set. And in order to actually truly see how your model performs on new data, you need to hold out a third set, which can then be your people call them different names. In the books, they called this the validation set. So they had train set, test set, and then the third set would be your validation set. I've typically heard that flipped. Um, but just know that you split your data up into potentially three pieces, and you use one of them in order to optimize, and then you use the last one as your sort of final evaluation of its performance. And so you do this so that you don't end up kind of spoofing your numbers on unseen data by optimizing for the set that you're measuring performance again. Um, Question in the chat. How could we know they don't occupy more space, more bins? If we knew this, we could then use something like PCA to make learning process faster.
If you want, I can try and jump on this one.
Sure.
So basically, what people often say is that if you look at MNIST or images or text or whatever, there's so many exponentially many possible values, but realistic ones, the ones that we care about, is usually a much smaller set. If it was a linear subset, you're absolutely right. You could use PCA and you could eliminate a lot of that unnecessary dimensionality. Usually people think that it's a non-linear subpart of all the space. And so that's why they use the term, it's on a submanifold. So this manifold may have curves and wiggles and whatever. And so PCA won't work. You need something else. If it was a super regular manifold, if you knew it was somehow, I don't know, whatever, circular or something, you could use some technique. But if it's just this arbitrary thing where we're doing images and dogs have certain things, they're always going to have four legs, they're always going to have two eyes. You may not be able to see them in a given image, given angle, what, but like has those properties. But in a different part of the space, birds have two legs, and they have wings. So it's not this completely regular pattern. Then knowing that it's a it's a lower dimensional manifold is a useful abstraction, but you don't necessarily, I don't think, have any way of extracting that other than you train the model. And then in theory, once the model's trained, if you have enough data points, you could try to use some like, UMAP, t-SNE, whatever, to try and like tease out something about what the contour of that manifold is. Hope that helps.
And
It's a good question.
one example of that. So imagine you have a whole bunch of images. So like it can be cats, it can be dogs, it can be whatever. If you look at the actual underlying data, it's a whole bunch of pixels that have continuous values that can be certain things. How many of those possibilities actually make real images? Not actually that many, because a lot of them, like if you were to just sample random noise for every single pixel, you're just going to end up with an image that's noise. There's a very small subset that actually makes like this is a picture of the world versus this is just static. And so that's kind of one of those examples of like this is a very small constrained subset of like there's actually tons of possibilities, but the amount that fall in your space are much less than that, actually.
So Ryan, going back to the slide, I was thinking about there was this Kaggle competition that I was working on, and uh, you know, after a while, some of the advanced people were saying, I think there's a bunch of easy examples that are very easy to classify. There's actually a very small number of hard examples that we need to get right. And so basically, what Ryan was saying is that if you tweak your hyperparameters or whatever, you can get it so that you're getting all the hard examples in the training set right, but you have no idea if that generalizes because it was just so few. And I think for a lot of people beginning in machine learning, it's not obvious until you stop, you pause, and you think about it that running a training, running another training, like tweaking things and running another training, that's um it really is overfitting because you have those held out examples and ultimately it's not literally the same as if you just trained on those held out examples, but if you imagine doing infinitely many of them, it's basically the same thing as just training on your held out examples, which is going to give you the same problem. You're not actually validating anymore.
All right, so that's the end of the slides. I can pull up the book. we can look at some problems. I don't
Yeah, the
know if,
problems for this chapter were a little bit weird. There's like one or two we can discuss, and then the others it's just sort of like calculate a bunch of stuff or let's look at this high dimensionality stuff.
yeah, yeah. This first one, does anyone want to take a crack at answering this? So will the multi-class cross entropy training loss in figure 8.2 ever reach zero? So if we go back up to this one, so will this loss ever reach zero? Why not? Open to anyone.
No, because when you do the training, it because like if you think of the gradient loss, you can kind of like approximate zero, but you can never get exactly to zero. Because like because like the process of you apply the gradient loss and just multiply it.
Yeah, yeah. So you're taking all of these little steps and you might get very, very close, but you never hit exactly zero because you're moving around the space. Um, there's
Okay.
potentially other scenarios where you also don't hit zero. I don't know if anyone wants to guess at those.
Um, the problem is that we have smooth curves and we approximate them with lines, pieces of line, segments. So in whatever we try, we cannot actually smoothly approximate curves with lines.
Yeah,
Yeah, and I can also add that if you do cross entropy, if you just look at the way the model is constructed, the model outputs logits for each of the 10 classes. Okay. And then you do a softmax, which is e to the whatever power. And then for each of those 10 things, you do e to the whatever. And then you sum up those things and you divide by the sum so that everything adds up to 1. So the only way you could get a zero loss is if you had e to the something for the correct answer and you had zeros for everything else. But e to the something is never zero. Even to the negative 1,000, it's still not quite zero. So I guess you could get a floating point underflow maybe. But theoretically, you can never get there because no matter how small the number you output, e to the negative zillion is still not zero.
yeah. I don't think that this happens with this specific data, but it's also potentially possible that you can have the same inputs and a different output. That's kind of an unfortunate reality in a lot of data. You might have, if you're doing something that's looking at demographics of people or something, you take their age, height, weight, and you're trying to predict something about them. There's going to be multiple people with the same age, height, weight, but then they might have a different output outcome. And so it's physically impossible for the model to even represent that because it's the same input and you're expecting a different output. So just another piece to that puzzle. And that was something that they actually talked about in the chapter was that sometimes you don't have all of the variables necessarily necessary to describe something. So if you're only given someone's age, for example, but you needed those other two variables in order to differentiate the people, then your model cannot have the capacity in order to make those predictions. Very often, you have to go searching for the features that are actually useful for something because if you only use features that don't describe why something's happening, then you can't hit that perfect loss. Um, any more questions? So I thought 8.4 was decent. I don't know if anyone wants to take a crack at that as well. So consider the curve in figure 8.10b at the point where we train a model with hidden layer size of 200, which would have 50,000 parameters. What do you think will happen to the training and test set performance if we increase the number of training examples from 10,000 to 50,410? So if we gave it more data, what do we expect to change in this graph? So right now it's given 10,000 data points. If we gave it 50,000 data points, what would we expect to train with the training set and the test set?
I guess this dashed line would move to the right.
Yeah, so you would need more data in order to hit the, or you would need more
To
parameters
memorize,
in order to memorize the data.
Yeah.
So you have more data, so you need a bigger model to memorize it. Yeah.
Yeah, the question actually says, what do you think will happen at the 200 size model? And I think the idea is that the dotted line, like you say, is going to move right to approximately there. So even though you added more data, whatever, then your 200 model might actually be worse.
Yeah, you might end up at the wrong spot on this curve.
So what you were saying, Ryan, earlier is generally we're as far to the right as possible as we can be. We want as big a model as possible just based on our compute budget. So under those circumstances, if you get more data, it generally can only help. This is the sort of oddball example where your model size was not that big. It was 200. And so the size of the data could have gotten you right into that critical region. But I think that's sort of the general idea behind what you were saying, Ryan. Why we do that is we want the best performance. And if you're at, 100 million parameters, then you don't really have to worry about the possibility that your data is, at doubling your data is always a good thing because you're never getting to where it's like just barely big enough model to understand it.
Yeah.
I hadn't thought about that possibility, Ryan, until I read it in the book, that like you could add data and your model performance could actually get worse. So like I see now that it's like a logical possibility, but practically probably you almost never run into that.
I don't feel like it's difficult. I would have to try it and prove it myself because I just don't see a reality where going from 10,000 points to 50,000, you would end up getting worse data because I would think that you would just fill in your space so much better. But I guess in theory, your model just doesn't even have capacity to take advantage of it.
Yeah, and also you and I were so trained to regularize that might not even happen once you regularize heavily enough.
Yeah.
So like if it was an image model, if we do all these augmentations, flips and rotations or whatever, then we probably are safe. It's like it would be like that very first picture we saw where the test loss, it never went back up. It just stayed flat,
Yeah.
So yeah, in real life, I don't think you need to worry about it, but I thought it was an interesting, just sort of like mathematically, yeah, I guess that's true.
Yeah. All right. I think that's it in terms of the useful problems. The other ones are, I would say, not even that related to measuring performance.
Yeah, I do think though that understanding the curse of dimensionality does come up sometimes. I'm having trouble thinking of an example, but the thing you need to know is you cannot rely on your low dimensional intuition when dealing with high dimensional data. So 3 dimensions definitely can't. But the reality is, even if you could somehow think in 5 or 6 dimensions, that's still not going to be representative. And gosh, I can't remember, but I remember once, I was in a paper reading group discussion and we were talking about a certain paper and people were asking about like a certain something and they're like, oh, well, it would just, and I was like, no, that's not the way it works. The curse of dimensionality is that when you have these like 32,000 length vectors, you can't say that like you can't do like k nearest neighbors because like every point is approximately equidistant to every other point. They were making some sort of argument about like near neighbors or whatever. And it's like, no, the differences in distance between any 2 points is so minuscule. And so I just thought that like, yeah, maybe it's not that important to training neural networks directly or whatever, but it's always good to understand that there's some very weird things in terms of the points being somewhat equidistant, the points all being orthogonal to each other, all these kinds of things. All right. Oh, looks like there's a question in the chat, Ryan.
Yeah, is there any experiment between the performance and 10%, 20%, 30%, up to 100% training data? I've seen plenty of those experiments, but it's always been in the case where the model has enough parameters where it can just take advantage of those. So I haven't necessarily seen something where it's like spanning the capacity of the model. Typically, you would have to scale the model a lot further down than most people do. So I I haven't personally seen it. I bet people have done that research, but I haven't seen it.
Yeah, so in our regime, it always gets better the more data you give it. Ryan, can you talk about why it is that then if you're doing something like cross-validation or whatever, after you've set all your hyperparameters, you may be using only like 80% of the data if you're doing 5-fold. So exactly to the point of the question, you then retrain with 100. Can you kind of walk through that?
Yeah. Yeah, so one of the things that they mentioned in the book is that the process that we talked about, the train set, the test set, the validation set, that's one way to split up your data, and then measure performance, that they call cross-validation. And then the kind of next step beyond that, people call k-fold cross-validation. And what you do is you split your data into k-folds potentially. So that can be typically 5 or 10 or something like that. So you split your data into 10 pieces, and then you will fit on 9 of the pieces and then measure performance on the 10th or something like that. And then you can do that 10 times, and then you've trained against all of your data and you validated it against all of your data, because you cycle through all of those different folds. So you train 10 models, you measure the performance of all 10 of those models, and then you can get sort of an estimate out. And that's a good way to get a very robust estimate of what your accuracy is going to be. But then in the final, like, actually send this model to production time, or if you're doing a Kaggle competition or something like that and trying to squeeze the last percent out, what you probably want to do is actually train against your entire data set. So throw your folds away, just say train against the entire thing, and now you got an extra 10% data because initially you had that set aside for validation. And so you'll see a small 1%, 2% bump in performance just because you gave yourself 10% extra data, and you use that k-fold process to measure your performance, and then you use the full retraining in order to get the best performance possible. So the k-fold in that case is just for like estimating what your performance would be, and seeing how it is expected to perform, and then you can get gains from just adding in all the data, basically. Is that what you were asking about, Ted?
Yeah, because I think that books will teach you how you can do k-fold, but they don't necessarily mention the part at the end where after you've gotten an accurate estimate of performance, you want to use all your data, which is I thought was exactly where the question in the chat was going, is that like, yeah. So I thought you clarified you will see a small bump because you're giving it more data.
Yeah. And so that it's kind of funny because on Kaggle, there was a team that was consistently having success and they kept winning. And it was like, how do they always just end up 1% better from everyone? And that was one of their, like, it's such a minor detail, but that was one of their innovations is like, they just had to be a little bit braver than everyone else and say, I'm going to train against all the data and just blindly submit, because what everyone else was doing was they were just always measuring their performance. And they said, we know how our performance is going to be. We're going to train against all the data. And that gave them small marginal increases. So
Yeah,
it's a
that's what I
valuable
do.
trick.
That's what I do there too.
Yeah.
Any other questions? All right. We've got office hours in 5 minutes. Ryan, do you want a 5-minute break to rest your voice, or do you want to just jump in and start early?
We can take a 5-minute break just for people who join late.
Okay. All right. So we'll actually we can stop the recording here.